Hi, welcome to the Calculus 2 lecture series. We are in the unit number 4, sequence in the series. This is the second video for the lecture number 24. Talk about the Taylor and the Maclaurin series. For our first video, we talk about the definitions of Taylor and the Maclaurin series and how to use the definition to construct a Taylor and the Maclaurin series. And today, for the second video, we're going to continue this thought and we're going to take a look for some existing series. How can we get the Taylor and the Maclaurin series and by using some existing series here. All right, so now let's take a look. Okay, so where we stopped on the video number 1 here. So we talk about, we wrapped it up, the video number 1, by doing the problem number 4. We say find the Maclaurin series for the e to the 4x. And then remember, when we first start, I give you a list of the most commonly functions, the Maclaurin series. So we say for the e to the 4x, you can use the definitions and try to get a Maclaurin series, or you can just say, hey, I already know the Maclaurin series for the e to the x is 1 plus x, and then we just can replace the x with 4x here, right? Okay, so let's follow the same thinking for this methods here. Now let's take a look here. I want to find the Maclaurin series for the f of x to the 1 over x. We have several different ways to do it. So let's try to remember in the 11.9 on the lecture notes number 23, we said we can manipulate a geometric series and then we can derive the a function by manipulate the geometric series. Now we can write that function into a power series. All right. So okay, let's take a look. Let's try to so now let's kind of refresh, right? So the geometric series, we know what is a geometric series. We know if it's a summation n from 0 to infinity to the xn. And if x, of course, x need to less than 1, right? Now we know this ones here will be what? This one will be 1 over 1 minus x. That is what is the geometric series about. Okay, so now let's try to see. I want to find the f of x here. This is 1 over x. How do I manipulate the geometric series? We can say this one here is 1 over, then this is 1 minus x here, right? So if you manipulate that, then what is here? This is 1 minus x is similar to the geometric series here. You replace the geometric series with the 1 minus x here. So now I can rewrite it back to the geometric series. So what is my purple x is right now replaced by 1 minus x, the yellow x, right? So now I can say this is n from 0 to infinity. Remember, this is the purple axis, right? So now what is my answers here will be 1 minus x to the what? To the nth power. Right. So this is how do we manipulate the geometric series, because we know the sum of the geometric series. Okay, now let's take a look at how do I do the so from the other ways, like I said, you can find many different ways to do it, right? So we said the second part, they say, hey, how about using Maclaurin series for the natural log 1 plus x? So let's go back to a table, take a look. What is the Maclaurin series for the natural log 1 plus x? It's x minus x squared, and so it's an alternating series. It's 1, 2, 3, 4, right? Okay, so now we can, write these ones here, right? So, so now let's go back to here. So we said from the table, so let me write here, so in different color. From the table, we have in the beginning, so I know the natural log 1 plus x is equal to the summation n from 1 to infinity and this is the n negative 1 to the n minus 1 x to the n, right? So this is from the existing, the existing Maclaurin series. If you want to derive it, it should be pretty easy. Okay, so now I'm really looking for is f of x is 1 over x. So how is this going to work? So I will say, how about I differentiate the natural log of 1 plus x. All right, so on both sides here, so that means that when you do, because I know the natural log is here, right? So when you do take the derivative of the left-hand side will be what is 1 plus x. Then you need to take the derivative of the right-hand side, so you can go inside and take the derivative. So what is this one here? So this is n, the negative 1, n minus 1. Then the x to the n, you times n. So what is here? X to the n minus 1, right? Because you take the derivative, so your n restart with where? From the 1 to infinity. And then in here, the n cancel out. So now you will get the 1 plus x is equal to what? 1 plus x is here will be equal to, okay, so this will be equal to summation n from 1 to infinity, and this is negative 1 to the n minus 1, x to the what? N minus 1, right? Okay, so now let's try to manipulate it. Now I know this one's here, right? So now I'm looking for is this 1 over x, right? Okay, so let's say the 1 over x, right now I need to be the plus, right? Okay, so I will say this one will be 1 plus x minus 1, correct? Okay, so now take a look here. So then this is your new x, 1 plus x. And just like the one, this one is your purple x here. Okay, so now let's try to put back to the my series. So this is x minus 1, right? So here, let's see here. So it will be summation. Okay, so this is will be the summation n from 0 to infinity, and so you will have a negative, right? So you have a negative x minus 1 to the nth powers here. Okay, so now if you want to move the back here, so you switch the negative sign, so negative become positive. You can say this is a summation n from 0 to infinity 1 minus x to the nth powers here. Okay, so that is how can you do that, and by using the existing Maclaurin series, and you can find the, you can find the 1 over x here, as you can see here, right? So you both will get what? Both will get the same answers here. Okay, so one is you using the existing Maclaurin series, and then the one is you use the, like the here we know the Maclaurin series for the natural log 1 plus x, and then you can just manipulate it to match it. Okay, so now let's take a look. How do I find the Maclaurin series for the x over 1 plus x squared? All right, so in here, this one here is the same things here. You can use definition, but then probably the derivative will be pretty tedious. So I'm still know is like n from 0 to infinity x to the nth power. This is by the geometrics, right? So it's over 1 minus x here. So let's take a look here. The first one's here. So okay, so the first one's here, you will have 1 over 1 plus x squared. Okay, so let's do a little bit. So it's 1 minus negative, right? So it's 1 minus negative x what? So this is 1 plus x squares, right? So I can treat this as 1 minus x square here, correct? And now let's take a look at what is my purple and yellow. So this is your new axis here, right? So your new x replace with this purple axis here. Okay, so now this one's here, I become summation n from 0 to infinities, right? So what is here? This is negative x squared to the nth powers here. So when n is equal to 0, take a look at what you have here is 1. N is equal to 1, you have x to the square. N is equal to 2, you have a positive x to the 4th, right? So you have an alternating series. When x equal to 3, n equal to 3, you have x to the 6th, right? So that's what you have. You have an alternating series. Now I still have an x on the top, right? So what I need to do here, I will need to say x to the 1 plus x squared will just be the x times 1 minus x squared plus x fourth minus x sixth, da 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 da. So I will have x minus x cubed plus x fifth minus x 7 and down. Okay, so now let's try to write it into the series form. So right now, my exponent is odd number, right? 1, 3, 5, 7. So I will say from the n from 0 to infinity. Then I have, I need to save a space for my negative ones here. Okay, so now my x exponent can be 2n plus 1. So when n equal to 1, when n equal to 0 is 1, so that's fine. So what is negative 1 mean? All right, so when when n equal to 0 is a positive. Oh, so here I just put the n will work. So when n equal to 1 is negative. All right, when n equal to 2 is a positive. So this work. So I know I'll be able to, find the Maclaurin series by, existing manipulation. So first part here is you find the geometric series, right? And then you just multiply it. Okay, so let's take a look at our next examples here. This example is really a very interesting example because we know try to find the sum of the series. It's a very difficult job. And most likely, the one we only know is the geometrics. We can find exact the sums here, right? So how do I use the other techniques try to find the sum of this series here? Okay, so the first thing is here, this is n from 1 to infinity. So it's this needs take phi to the nth power n, all right? So let's take a look here. So this one here is really, so it's when n equal to 1. So you can kind of separate that. It's n equal to 1 to infinity. So this is negative 1, right, to the nth power. And then this is the 0.5 to the nth power to the nth here. Okay, so this one's here is very similar. Okay, so this is negative 1. So now if you take a look, go back to my existing. Okay, so go back to my existing and the Maclaurin series to see which one looks very similar. So I see here, this must be alternating, positive, negative. So it looks like this one's here, then I have the denominator is n. So here, the natural log 1 plus x seems it's match very well, right? So in here, the natural log 1 plus x is this forms here. So let's see if we can match it. Okay, so in here, okay, so kind of here, let me try to put it here. So remember here, the natural log 1 plus x by the existing Maclaurin series. So I think I already wrote it one times, right? So here, right? So it's n to the negative 1, okay? So I have, this is n, to the negative 1 to the n minus 1, then x to the n. Okay, so if you take a look, if you compare, okay, n to n match, okay, x, okay, so xn to the 0.5n match. The only thing off is this negative 1 and minus 1. So I would say, okay, now I want to use the natural log. So I would say this one here is n from 1 to infinity. Okay, so I have n. So I take out 1 negative 1. So what is this one here is n minus 1, 0.5 to the n. Okay, that's great, right? Because if you take a look here, what is this part? This part is exactly match what is Maclaurin series of the natural log, right? So now I can put this negative 1 out. Then I will say here, this is n from 1 to infinity. So this is n, this is negative 1 to the n minus 1, 0.5 to the n. So see here, right? So they exactly, okay, so this one's here is exactly match what my definition about the natural log. So what is my answer here is a negative natural log. What is my x here is 0.5. So it's 1 plus x here. X is 0.5 here, correct? Right, so the in here, right, so the x here, right, so the x here is a 0.5 here. So I find the answer for this series here. So this series is equal to the negative natural log 1.5. Okay, so if you want to find the values here, you get that this one is very close to negative 0.4054. Okay, pretty cool, right? Okay, let's take a look at our last problems here. So this is the same way. I want to find the infinite series expansion for this one. So I want to find the integration value. So how do I find it? And then how do I find the series, right? Okay, so now in here, so we still, from the basic, right, we still know my geometrics here is always is the 1 over 1 minus x equal to the summation x ends, right, n from 0 to infinity. Okay, so now let's start with here, okay? So this is 1 over 1 minus x cubed. Haha, so this one's here, this is my new x to my geometrics x here. So I can rewrite this to what? This is the summation, so what? X to the cube to the nth power. Am I right? So this is n from the 0 to infinity. So I will have n from the 0 to infinity x to 3n. Okay, x to 3. Now I integrate both sides. I integrate, this is 1 over 1 minus cube dx. So it will be the similar when I integrate in here, right? So x to 3n dx. Okay, so now this one become pretty easy because I know how to integrate the 3n. So it will be the 3n plus 1 x to 3n plus 1, all right, and the plus c. And now, because we have this boundaries here, right? Okay, so now I need to put the boundaries here. So the boundaries here will be 0 to the 1/2. This is 1 minus x cubed dx. All right, so it is the same thing. So it's a summation n from 0 to the infinity. So x to the 3n plus 1 to the 3n plus 1. So the top, I'm going to put 1/2 and 0. Correct? So when the x equal to the 1/2, so this will be summation n from 0 to the infinity. So this is 3n plus 1. So this is 1/2 the 3n plus 1. Then minus 0, right? Because when you put a 0 into the x's here. All right. So now this is what the, so if you want, so this is the what we have. So you can simplify it a little bit. So this one will be a to the, I think 2 to the 3 is an. All right, so an, and then you have 1/2 2 times the 3n plus 1, right? Because 1/2 of the 3n plus 1 is equal to the an, right? So it's equal to the an times 1/2. All right, so that's why here we have an n from 0 to infinity. So this will be 2 times 3 is 6n plus 2 to the an. And this will be my series. So I can rewrite this integration into an infinity, the sum of the series, right? All right, so that's it. And that is for the part 1 for this lectures here. We know how to do the Taylor and the Maclaurin series, and by the definition, or if you have an existing the series, and you can manipulate that to become Taylor or the Maclaurin series, or you can use like I told you before, the table I give you here, those are some Maclaurin series. It's a commonly used function Maclaurin series, and then you can manipulate your function and try to match here, and then you will be able to get the series out, a lot easier than by using the definitions. Okay, all right. So now let's our next topic we're going to talk about is, we call this the Taylor polynomials with degrees n. What is that? That will be our next videos. All right. So nice talk to you and have a good day. All right. Bye bye.